Calorimetry. So calorimetry is a way of measuring the amount of energy gained or released by a reaction. So a reaction could be anything from I'm simply changing the temperature. I'm either cooling down a hot piece of metal, or a reaction is giving off energy and I want to see how much energy it has released. It could be a state change. How much energy does it take to melt an ice cube, or how much energy is absorbed when I'm making a state change from a liquid to a gas. Or it could be a chemical change. How many calories are in a Snickers bar, right? They do this in a calorimetry. And the way that a calorimeter works is that it's basically a container, and it has an amount of water in it. And that amount of water has a known mass and a known initial temperature. And we always know the specific heat of water. And that's a fairly insulated container. So labs that really depend on having good calorimetry calculations will have great insulation. And the reaction occurs in that water, usually in a container that gives off the heat or absorbs the heat from the environment. So there's a big assumption, and the big assumption is that there's a complete energy transfer between the reaction and the water. So the first example is if I just have a temperature change. So the example is I have 60 grams of a metal, and it has an initial temperature of 95 degrees Celsius. It's placed in 150 grams of water that has an initial temperature of 20 degrees Celsius. As the metal cools, the water temperature rises to a final temperature of 25 degrees Celsius. What is the specific heat of the metal? So one of the things that you have to assume is that whenever I have a hot object and a cool object, the hot object will cool down, the cool object will heat up as energy is transferred until they end up at the same temperature. That's when the energy transfer is complete. So the energy gained by the water has to be equal to the energy lost by the metal. And this is absolute value. Right? In reality, energy gained by the water will be a positive value because it's endothermic, and the energy gained by the metal lost by the metal will be exothermic. It will be negative. But I can't have a positive value equal to a negative value, so we're just going to make them both positive. I'm looking for the magnitude, not the direction of heat transfer, right? It's a vector quantity. So to make my life easy, and what I would suggest to you is find some way of making sure that you keep the metal stuff with the metal and the water stuff with the water. So I've circled anything to do with the metal in green, and anything to do with water as purple. And if there's something that's the same, it's purple and green. So the energy gained by the water, all we're doing is an increase in temperature or a decrease in temperature for both. So I'm going to use the equation mc delta T for both. Except the masses and the specific heats and the temperature changes are going to be different. So for the water, the mass is 150 grams. The specific heat for water is 1 calorie per gram per degree Celsius. And the delta T is 25 minus 20. So it changed temperature 5 degrees. The metal has a different mass, 60 grams, and I don't know what the specific heat is, but the change in temperature is much larger. It's going from 95 to 25 degrees Celsius, or a total of 70 degrees Celsius. So when I make those calculations, I get 750 is equal to 4,200 C, divide both by 4,200, and I get a specific heat of 0.18 calories per gram per degree Celsius, and it's in green, because that's the specific heat of the metal, right? So in order for the energy lost by the metal to be equal to the energy gained by the water, the specific heat of the metal has to be 0.18. And always check for logic. So the temperature change from the water only went 5 degrees Celsius, which is a lot less than the temperature change for the metal, which is 70. This should be 70 degrees Celsius. And the mass of water is much greater than the mass of the metal, so it makes sense that the specific heat of the metal should be a lot less than the specific heat of water. The second example, heat of reaction. So here I don't have a temperature change in one of them, but I do have a temperature change in the water. So the water will at least have a temperature change. So I have 30 grams of a piece of food is combusted, so that's a reaction, it's combustion reaction, in 200 grams of water at a temperature of 20 degrees Celsius. The final temperature of the water is 45 degrees Celsius. This is exactly what we're actually going to be doing in a lab, except we're not going to combusting food, we're going to be combusting a candle. So the candle underneath will heat up the water, we see how much the water increases temperature, and we calculate the heat of combustion. So again, purple is going to be the food combusted, and the green is going to be the water. So I know everything about the water. Its mass is 200, specific heat is 100, and the change in temperature is 45 minus 20. Change temperature by 25 degrees. For the metal, I know the mass, I'm looking for the heat of combustion. Notice that there's no temperature change because it's a heat of reaction. Heats of reaction, whether it's state change or anything, aren't going to have changes in temperature. I'm going to substitute X for heat of combustion. So I get 30X is equal to 5,000. And so the heat of combustion is 166 calories per gram. So remember, no delta T with the combustion, purple and purple. The delta T will definitely be there for the water. All right. This is an example for honors chem only. So this is where I'm trying to find the final temperature. So 60 grams of a metal with a specific heat of 0.8 calories per gram per degree Celsius and an initial temperature of 90 degrees Celsius is placed in 150 grams of water that has an initial temperature of 25 degrees Celsius. What will the final temperature be? One thing to remember is that the final temperature of both the metal and the water will be the same, right? Remember to make the delta T a positive value. I just want to know what the range of temperature change, the magnitude is going to be. So 60, so the metal, 60 times 0.8 times the quantity 90 minus TF. That's my change in temperature. And I need to put 90 in front to make this a positive value, is equal to the mass of water times the specific heat of water times its change in temperature. And these TFs will be the same. So then I multiply out through, I isolate my variables, and I solve for my variable, and it turns out that my final temperature is going to be 40.8 degrees Celsius. Now you check for logic. Does that make sense? Well, I know that my final temperature has to be between my coldest temperature and my hottest temperature initial. Right? It's not the case where I'm going to put a hot piece of metal into the water and the water will actually get cooler. Or it doesn't make sense that I put a hot piece of metal into cold water and the metal and the water gets even hotter than the metal was. Your final temperature should also be closer to 25 degrees Celsius because the specific heat of water, 1, is larger than the specific heat of my metal, and the mass of my water is also greater than the mass of my metal. So for these two reasons, I would expect my final temperature to be between these two values, but closer to 25, and 40.8 is indeed closer to 25 than it is to 95. The second example for honors again only is a state change with water. So if I have 60 grams of a metal at 160 degrees Celsius with a specific heat of 0.4 calories per gram per degree Celsius, and I place it in 100 grams of water at 95 degrees Celsius, how much of the water will be vaporized? So the water is not just increasing in temperature to the boiling point, it will undergo MC delta T, but I'm also including a state change because I'm asking how much will be vaporized. So the assumption here is that not all the water will be vaporized, so the final temperature for both substances will be at 100 degrees Celsius. Remember that the temperature does not change during a state change. So the E given off by the metal is just going to be MC delta T. It's not changing state. It's going to be a solid all the way through. Mass is 60, specific heat is 0.4, and the change in temperature is from 160 to 100. So 2,400 calories is given off by the metal. The amount of energy that is needed to raise the temperature of the water is going to be MC delta T. So I have to raise the temperature of the water to 100 degrees Celsius in order to start boiling it. So remember that I have to be at the boiling point. So 100 times 1, M times C, times the change in temperature. I'm only changing the temperature 5 degrees, so it doesn't take much energy, 500 calories. So of the 2,400 calories worth of energy that's released by the metal, only 500 calories is used to raise the temperature of the water to the boiling point. So the remainder, 1,900 calories, is available to boil that water off. And that's going to be E times M times heat of vaporization. Now, I don't know how much water I can vaporize, so that's what I'm solving for. I know my heat of vaporization is 540 calories per gram, so the remaining energy that's left over, 1900 calories, will be used to boil off whatever I can. And it turns out that it's a really small 3.5 grams. So only 3.5 grams of the water is converted from liquid to gas. The remaining 96.5 grams, 100 minus 3.5, will remain at water at 100 degrees Celsius.